Okay, Algebra 1, I'm going to break the review guide for Quiz1c into 3 separate video lessons. And the one that you're going to watch right now is about the big picture of algebra, as I called it. The others will be in separate videos. That way, later in the year, if you want to come back and just study one of these topics, for example, this one being the big picture of algebra, you can always come back and just see this video and not have to watch a longer video. So this whole big picture was presented on page 23, or actually we talked about it first when we talked about the age puzzle, and then we talked about some other examples, for example, the Toothpick Mountain story. But the basic concept here is, how can you use algebra to describe a pattern? You see that there's a pattern. How can you then use algebra to describe that pattern? We're going to get even farther than that, though. We're not just going to describe the pattern, we're going to make use of the pattern, and you'll see that in this lesson that's on page 23. So the first task was to take the 4 figures, 1, 2, 3, and 4 that they gave you, and draw the 5th and 6th figures in the sequence. So I've gone ahead and done those kind of in a rough way here for 5 and 6. I didn't actually make more blue blocks. Instead, I just kind of filled them in. But you would have, if you'd done this yourself, you would have made the next diagonal of boxes, and then for figure 6, the next, again, diagonal of boxes. And then the step 2 on the page was to use a table, or actually fill in a table that they had started for you in this case. And so notice that what they've done in this table is they've written down what the perimeter was for each of the 4 figures. And let's just make sure that this is clear what we're talking about when we say perimeter. It's the spaces that are taken to walk around the outside of the figure. So 1, I can't do this very well with this cursor here, but 1, 2, 3, 4 sides, and that's what they have here, is the 4 sides. So you continue on here, and you're going to see, if you do this for each of the first 4 figures, that it takes 8 steps to walk around this one, and as it says here, 12 steps to walk around this one, and lastly 16 steps to walk around this one. And when we talked about this in class, everybody who came up to the board showed they had recognized that each time what had happened was that they'd gone up an additional 4 steps. So then people were able to fill in what the perimeter would be for the fifth figure without even actually having to count it off. And they were able to say that it would be 20 for the perimeter of the 5th and 24 for the 6th, simply adding 4 each time. Now, when we talked about this in class, we talked about the idea that it would be nice to turn that growing perimeter that we're seeing here into a pattern that we can use again and again. And if we don't do that, then we're going to have to be forced either to draw more figures, like we have here. We've drawn to the 6th, but it's going to get to be pretty big and pretty time-consuming to make a 7th, let alone a 17th, or to extend this table out by adding 4 each time. And that could get pretty time-consuming if we got to the 17th in the table, let alone the 77th. It would really be nice if we can turn it into a pattern. So what we noticed in the class was that the perimeter for that first figure was 4 times 1, and what we started to notice was that there seemed to be some relationship to what stage we were at. This is the first stage, if we want to call this figure 1, or similarly figure 2 is stage 2, and all the way out here figure 4 is stage 4. There's a relationship between the stage we're at and the perimeter, and that is 4 each time, 4 times the stage. So 4 times 1 made that 4 here, but similarly 4 times the second stage made 8 steps around the perimeter here, or looking all the way out here to the 4th stage, 4 times the 4th stage made 16 steps around the perimeter. That way, we were not only able to fill in 5 and 6 like this, and say that the pattern here is 4 times 5, or in other words 20, and 4 times 6, or in other words 24, but we could go even farther, and presumably it would be 4 times 7 for the 7th stage, or all the way out, 4 times 17 for the 17th stage. In fact, what we were asked to do was to figure out what was the perimeter of the 25th figure. And following the pattern here, it's going to be 4 times 25, or in other words, 100 steps around the perimeter of that figure. So the final question that we were asked was, no matter what the perimeter of the figure is, so let's just plug in an n for any number that we want, what would be the perimeter? What would be the pattern? And that turned out to be 4 times n. And in this case, we just used n for how many stages we had. So whatever your favorite number is, whether it's like we said 7 or 17 or 70, you can plug that number in here for that stage, and you can figure out how many steps it would take to walk around the perimeter of it. So for example, if your favorite number was 70, 4 times 70 is 280, and the perimeter of the pattern would be 280 steps. Okay, let's make sure this is clear by trying it again with a different set of figures. So on the same page, farther down on the page, they had us copy down this sequence of 4 figures going from 1 through figure 4, and then draw the 5th and 6th figures. And that's what I've done here. Again, I've represented them with x's and y's, but you can imagine that these were filled in with boxes instead. But those are the shapes that you ought to have drawn, roughly speaking, for the 5th and 6th figures. And the next thing you were asked was to calculate the perimeter for all 6 figures and organize those results in a table. Well, here's the table that I would imagine you would create. It's just like the table on the upper half of the page. You have the figure stage that you're at, like this is the 6th stage, and that's where we put stage 6 in the table. And then, just like before, we're looking at perimeter and pattern. So we went ahead and calculated, and we talked about this in class. People showed me they'd figured out what the perimeter was for the first figure, or the first stage, all the way through the 4th stage. And we'd said that it took 22 steps to walk around the outside edge, the outside border of this figure. And then we noticed that it seemed to be going up 4 steps each time in between, like 4 steps and 4 steps again. And then so presumably it would go up 4 steps here and 4 steps here. And so we were able to fill in the table here and say that it was 26 steps to go around this 5th figure without even marking them off, and 30 steps to go around this last figure here, again without stepping them off. So the next task on that page was this question: what's the perimeter of the nth figure? Now again, when they say nth figure, they mean no matter what number I put in there, is there a formula that's going to tell me what the answer is? Well, the first thing to do, whoops, didn't mean to do that, is to look back at the table we had before, where we were able to write down a pattern. And we'd said it seems to go up 4 every time. And we'd noticed the relationship here was simply 4 times the stage. So we're working all the way out here to the 5th stage. The pattern was that the perimeter was 4 times that 5th stage, which made 20. And so that's why we were able, for the 100th stage, the 25th stage, to say that 4 times 25 would make 100 out here, and that's what we were talking about. Well, that doesn't seem to work here, does it? Count these off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is those 10 here. And you can count them off yourself if you want for all the others. But the point is, there's not the same relationship here. Because before it was 4 divided by 1 is 4, 8 divided by 2 is 4, 12 divided by 3 is 4, 16 divided by 4 was 4. No matter what, it was really just 4 times the stage. Well, that's not true here. 10 divided by 1 is 10. 14 divided by 2 is 7, not the same number, so this is not looking good. 18 divided by 3 is 6. Okay, we're clearly off. If we want to keep going, 22 divided by 4, that's not even a whole number, it's 5.5. So we've got to do something different here. So let's step back. What is actually happening here as we look at the climbing number of steps in the perimeter? Well, it seems as though we started with 10, and then we added 4 each time. So some of the folks in class suggested that, hey, maybe that means the formula is the perimeter is 10, the starting place, plus 4 times every figure that we, times the number of stages in the figure. And so I put a question mark here to ask, is that really right? Well, there's an easy way to test it. Instead of putting f here, we can put the number of the figure in. Let's take 1 and put it in there, the simplest one. 1 times 4 is 4. 4 plus 10 is 14. Wait a minute, 14, that's not matching the perimeter for 1. And that won't work, as you'll find, if you try it for any of these figures. So this is not quite it. So then we said, well, maybe it's 10 plus 4 times f minus 1. Maybe it's one step before. And you might have written the formula like this. 10 plus 4 times f minus 1. Well, let's try this, but let's make sure that we do this according to PEMDAS. So again, if we take f is stage 1 and just put a 1 here, we would have, remember PEMDAS makes us multiply first. 4 times 1 is 4. And so I've got 10 plus 4, that's 14. 14 minus 1 is 13. Still didn't match the 10. So that's not quite right either. What we needed to do, and we figured this out in class, was we had to put parens around f minus 1. Now try it one more time. In place of f, we're going to put 1, and because we're at stage 1, and 1 minus 1 is 0. 0 plus 0 times 4 is 0, and 0 plus 10 is 10, and it does match. If you try it with 2, and I'm only going to, actually let's try it with something more complicated, 4. 4 minus 1 is 3. 3 times 4 is 12, and 12 plus 10 is 22, and sure enough it does match. This is the right formula, the right equation, the right description of the pattern that we have here. And so then we went ahead and filled it in. And you can try it yourself if you want for each of these, but what you'll find is all the way out to stage 6 here, or even all the way out to stage 66 or 666, whatever number you want to pick, this pattern will work. Okay, so let's bring this back to the question I asked at the beginning of this video, and the question that the textbook asked us on page 23. How can you use algebra to describe a pattern? Well, I hope that there are 3 things you've learned in this video. The first is that drawings are nice and can certainly represent a pattern, and tables are nice too, and in some ways are an easier way to organize and follow through with a pattern. But both of those have some limits. And if you can turn the pattern into an algebraic statement, an algebraic equation like this, it's going to end up being a lot more useful to you in terms of making predictions. The second thing is, I hope you noticed that often what you're going to do as you figure out a pattern, and this will be true for much of Algebra 1, is if you can look at where did you start? Well, we started with 10, and then how much did you go up each time? Well, we went up 4. That rate of going up, that rate of change, combined with the starting place, is going to be very important as we move forward this year. The third thing is be careful about calculating where you started from. Where you started from is what's in these parentheses right here. And we, oops, didn't mean to move that. We had to figure out that we didn't actually start where we might have liked. We might have liked it better if we'd started at stage 0. And in that case, we would have had 10 plus 4 times 0, or 0 is 10. But that's not reality. So you got to look really at how you relate where you start to this formula. And sometimes you're going to have to subtract something off of where it felt like you started to make the equation work. Okay, so that's, I hope, a good indication of the big picture of algebra. Algebra can be represented, like I've said from the beginning of the year, as pictures, as tables, as formulas, as stories. Later we'll talk about how it can also be represented as graphs. But the real power of it is the ability not just to write down what the pattern is, but to use the pattern to make a prediction.